Hey everyone, I wanted to talk about my system design for my engine system, and I finally got around to making the like kind of a rough draft of the architecture. So I'm using this app called Freeform. Have you all used that? It's on Mac. It's just like a kind of like a SketchUp kind of application. So I just use that. So I'm going to break this down piece by piece here as to what the system is currently. It's subject to change, and I'm going to show you where I anticipate most of the changes happening and what I want to add in addition to what's already there. So if we first come to the bottom section here, I have this wrapped in a Docker Compose box because Docker Compose is responsible for standing up my RabbitMQ server locally because it pulls the Rabbit image from Docker, and then it also is responsible for starting my .NET web application. So my .NET app is running on a Docker container, and as well as my RabbitMQ locally. So when I hit Docker Compose like up or in Visual Studio, you can just hit run and it'll run the Docker Compose script. So it's going to stand all that up. And so moving down here is my .NET web application, and there's two parts. So there's obviously the .NET backend. So you have your controllers, and all your services, everything you need. So .NET backend, and then it has a React front end. If you want me to go into the specifics of how you set that up specifically, I can definitely make a video of that. I might make a video of that honestly just to document it myself, so I can go back and reference it, because it's a real interesting pattern, and you can pretty much use whatever JavaScript framework you want to. Me in particular, I'm used to React, and that's what I'm most comfortable using, and I find that it just works really well. So I'm using a React front end, .NET back end. Connection to my back end is with just typical REST APIs, but also I'm using SignalR, so WebSockets, to handle like the real-time notifications that you saw a couple videos ago. For right now, this is one thing I want to change. For right now, I'm sending up data via just REST API to my controller endpoint. I want to change that because I have to increase the total throughput of data that I'm able to send. Right now, I'm getting about 1,000 per minute. I need that to be about 6,000 per minute before errors. So I'm going to be introducing possibly a WebSocket connection going from my client to my server. I'm going to try that as well as experiment with sending data directly to my RabbitMQ engines queue. So that's more to come on that. I just have to implement that. Once I do that, I'm going to update this architecture diagram with those two possibilities of data transfer as well, because I like to house it, or I like to contain it basically behind a setting to be able to flip to those if I need to. So moving up here is 3 RabbitMQ queues, one for my engine queue, which holds all the engine data that comes from my .NET web application. So currently the backend sends engine data up to the RabbitMQ queue. From then on, the engine data currently goes to my Rust microservice here. So you can see this flow here. Rust microservice consumes that engine data. I still have to kind of flesh some of these out, but for right now, it analyzes the engine data and sends notifications based on temperature. So the temperature notifications, you can see, flow down to this notifications queue. The notifications queue is consumed again by my .NET backend, which is displayed on the front end via SignalR. So that all happens real time, asynchronously, at the same time the engine data is being sent. So it works really well. Nothing slows down, and it displays it very reliably and pretty much near real time as it can be. So that's what that queue is responsible for. I'm calling it notifications, but honestly, it's going to be like notifications and commands, because I'm going to be using this to basically give you warnings as to what your engine may be doing, and also I'm going to give it basically shutdown commands, basically to say, okay, if we get a notification that tells us to shut down, we got to stop the engine and then stop sending web requests. So that's what that queue is going to be responsible for. So that's real important, and that's what all this microservice or Rust microservice does right now is basically look at the data and then make a determination based on the data. I'm going to be expanding this beyond just temperature, but that's just, for the prototype and for what I need right now, I'm just leaving it at temperature. But I have a bunch of formulas that I have to basically put into Rust to make, analysis and other things based on what the data the engine's sending. Another thing that the Rust microservice does, it also is going to send a log message down to the logging queue, and I just put this queue in and wired it up. So this queue is basically going to be our central repository for all of our logs. And I'm going to do this based on a log message with property source and message. So the source in this case would be Rust, and the message will be something like, logged engine overheated event or something like that. So that'll make its way down to this logging queue, and that's ultimately going to be consumed again by my .NET backend. But you can see here that my .NET backend is also sending a log message up to that queue. Again, I want this to be a central spot for anywhere any service should be able to see any logs, so that's why I'm sending it basically from my .NET backend to my logging queue and then to be consumed again. That's the only reason I'm doing that. So in this case, the source would be .NET, and the message would be like, I don't know, posted engine data or whatever it may be. And then ultimately, I'm going to be, when I consume these log messages on my .NET backend, I'm going to be displaying them on my front end again via WebSockets to build out a complete distributed tracing kind of graph to show you where the message has gone. I think this is going to work pretty well, but we'll see. Again, I have to do a lot of work to make that work. But I kind of got at least the skeleton of the infrastructure in place. You can see that I have another microservice up here. It's my Python microservice. I haven't actually made the temperature graphing on the microservice yet. I've been working on the QR code functionality currently. So the Python microservice is also going to be a subscriber to the engine queue. So when I'm going to publish a message to the engine queue, so that way it'll be consumed by both microservices. So the Python microservice is going to read that engine data and then graph. All it's going to do right now is just graph the temperatures. I don't want to do that in my Rust microservice because I see those as two independent things, right? My Rust microservice is making logical determinations based on the data, whereas Python is literally just reading it and then just displaying the engine temperature on a graph. And Python does that real well. It's got some good third-party libraries to do that. So I'm going to do that in my Python microservice. And then you can see that I'm also logging the message, or I'm going to be logging the message, or sending a log message again down to my logging queue. So you can see the interaction, hopefully, of all my services using these queues and how everything is interacting. So hopefully that kind of sheds some light as to what this system looks like currently. Again, this is a prototype. Everything minus the Python microservice is up and functional and running, which is really cool. And then this is where we just got to iterate on the design and make new decisions based on performance that we're seeing. But this is pretty up to date. I think this is honestly the current state of the system. Again, minus the Python microservice. I just added it in because I have it. I just haven't wired it to any of my queues. So once I do that and I actually have it running and sending and reading data from the queues, then I can just plug it right into my system. And this is really where the power of queues comes in, because it allows you to do asynchronous communication across microservices, and you can just plug in new microservices to the queues wherever you need. So it's super powerful. And again, you can just if we need to add more functionality, let's say we need to add I don't know, some kind of database extraction tool where we are extracting data from a database and transforming it or somehow. All we might have to do, honestly, if we want to do this, we could just add another microservice for ETL and then wire it up to our database or whatever we need to wire. So we can just keep adding components into this without actually affecting the existing system. Because you can look at this and you can put every single thing we're doing in here into a single web application and just make it a monolith, right? And then just, every time you make an update, you push the whole thing out, and that would work for sure. The downside of that obviously is you have riskier deployments because something you update might affect another part of the system that you weren't anticipating, so you might have to do a bigger rollback. You might experience slowness, especially with how much data we're sending if we're trying to send it all to the back end, especially if it's just a .NET API. So it would be harder to scale that because we'd have to scale everything. So harder deployments, harder to scale, and also it would make it harder for more people to work on the project at the same time if it's a monolith application, right? Because if it's a monolith and you try to just separate, concerns across people, you're going to inevitably run into merge conflicts, and you're all going to have to make sure that once your changes are all come together, that you test it again and then it makes sure it works. Whereas with this kind of approach with microservices, you could have somebody work on the Rust microservice, Python microservice, and then the .NET microservice all at the same time. And if the system is already in a functional state, then you can, each of those microservices can be rolled back, rolled forward again if they need to be deployed, all on different schedules and everything. So that's really the power of this whole system, or this pattern, I guess. There's not too much happening here. I mean, there's a lot obviously there's a lot happening, but this can get big really, really quick. And that's one downside of the microservice pattern, is that it can get out of hand really, really quickly, especially if you don't document stuff, because all it takes is, for somebody to not document a microservice reading something from a queue because it, might seem obvious in the moment, but then a year or 2 years down the road, a new team comes in, they don't know that service is talking to that queue, and then things just get crazy because now they have an outdated architecture diagram that they're trying to piece together how they think it works. Whereas microservices, you have to keep them the documentation as up to date as you can, and it's very important that you keep up to date architecture diagrams, just something to show you how the data is communicating. So obviously that's a disadvantage of microservices. There's a lot just more you have to internalize or understand, and obviously there's a lot more behind the scenes work to deploy things and to make sure that everything is talking correctly. So I get that. So it's a little harder to communicate across services when they're all independent. But yeah, so that is the state of the system. So if you have any questions, let me know. Again, we're going to be adding a lot to this, but this is the current prototype. So yeah, I'll see you on the next one.